What? Oh, right. Yeah. Cool. What?
Addendum. Last lecture too, the electric boogaloo.
Should we say that on the stream?
Before Amang starts his part of the lecture, I need to say a couple things about covering spaces. First of all, a correction to one of the statements, which was the universality of the universal cover, the fact that it's an initial object. So we proved that for the universal cover and any other cover, there exists a morphism of covering spaces in this direction. We didn't prove it's unique. Okay. For an initial object, there has to be a unique morphism into every other object, right? It has to be unique. We didn't prove it's unique, and we know it's not unique because, for instance, take the universal cover of the circle, take the double cover of the circle. Well, I'm sorry, but there's two ways to map it, right? You can map either all the even ones onto the top or the odd ones onto the top. Both are fine. Okay. It is unique, however, in a slightly different category. So let me introduce a category of pointed covering maps above M. So that means that we take so pointed covering spaces above M. So that means I have a cover above M, and I pick a point in it, right? E naught, whatever. Then in this category, there are many different universal covers, first of all, because you can pick many different points. But the morphism will now be unique because morphisms in pointed categories are required to preserve the selected points. If there's a point that was selected here and a point that was selected here, then this has to go here. All right. And in this category, now there are many different initial objects. In this category, let's say S1, right? Initial objects have the form, this is one, this is another one, this is another one, etc. Right? They are all different objects in this category. But they are all uniquely isomorphic, right? They are all isomorphic with a unique isomorphism, given by just mapping this point. Does
this fix the chirality issue?
We solved the chirality issue last time. Yeah. Okay, so there's many different, as opposed to the previous category, there's many different initial objects now, but they are all uniquely isomorphic to each other, as they should be. And this isomorphism also becomes unique because we fix the base point. Right. Now, if you go back to the old category, there's going to be only one initial object because you don't have to select the point, so it's just the real line for the case of the circle. The initial object is only one, but there's many isomorphisms of it to itself, right? Deck transformations that shifted it. So it's still unique morally, as a covering space. It's just not in the categorical. It's not initial in the categorical sense. Yeah.
Could you instead take in the skeleton of the category of covering spaces?
Instead of what?
Or would it be an initial object in the skeleton of the category of covering spaces?
Sure. Okay. And another note is maybe the last statement that I made. So the classification theorem of covering spaces. There were two statements that all. And I think I skipped this word. I don't remember. So all connected covering spaces. Connected covering spaces above M are in one-to-one correspondence with conjugacy classes of subgroups of pi 1 of M. That was number one. And then number two, all covering spaces not only connected and disconnected above M are in one-to-one correspondence with sets F with a pi 1 of M action. Okay. So for instance, if I take the set F to be, I take the circle and I take the set F to be 2 points, right? I can introduce the trivial action of pi 1 of M, which doesn't do any, just identity elements. Then what's the cover corresponding to that? Just two circles like that. Okay, but this one is disconnected. So some pi 1 actions will give you a disconnected spaces. And there's another useful way to reformulate this number three. All covering spaces of M are in one-to-one correspondence with homomorphisms let's call this H that goes from pi 1 of M to let me actually say all covering spaces with fixed fiber F. So let's fix this set F. And we can classify all covering spaces with that specific fiber in terms of homomorphisms from pi 1 to the diffeomorphism group of the fiber, which is just the permutation group of because it's a discrete fiber, just permutation group of the points. But only up to a global conjugation by some elements of this diff of F. So that means that if I have another homomorphism whose value on each curve is just this G H of gamma G inverse for all gammas, then that's an equivalence relation. Okay, first of all, what is this homomorphism in terms of that? No. By gammas, I meant the elements of pi 1. We don't need to talk about curves anymore, right? That we have a group we have its action on a set. How is that related to a homomorphism from by one of them into something? Right. So a pi1 action is what's called is basically a representation, right? It's an instruction for how elements of pi1 of M can permute elements of the fiber of F. Okay. So that means that each element of pi1 of M gets mapped to a diffeomorphism of F, right? A permutation of points of F. So a pi1M action is literally a homomorphism from pi1 of M to diff of F, right? That's what an action is. Okay. But, there's a subtlety, this one. Why is there an equivalence between some of these homomorphisms? So a pi1 action is not actually just a homomorphism. It's a homomorphism up to conjugation. Why? Not really. So I want to say that we have this fiber. It doesn't matter what we call these points, right? This could be point 1, this could be point 2. Like in the bundle, 1 could come, could correspond to this part, and 2 could correspond to that one. It doesn't matter, right? This is just an abstract fiber, just an abstract set. What we call those points does not matter. So I can shuffle the points within F arbitrarily, right? I can apply a global diffeomorphism to F. It's still going to be the typical fiber of my covering space, right? And it's not going to change the pi1 of M action on the fiber. Right. The typical fiber is just a manifold to which all fibers are diffeomorphic, but that diffeomorphism doesn't have to be unique or specified, or whatever, right? So we can just shuffle the points of F in an arbitrary way, and that gives me a conjugation on this homomorphism. So different homomorphisms are identified. And that's kind of similar, I guess, in spirit to this conjugacy classes of subgroups. Okay, and this map, so the map from covering spaces to homomorphisms from pi1 of M into diffeomorphisms of F, factored by this equivalence relation, is called the characteristic class of, when applied to a specific covering space, that homomorphism here is going to be called the characteristic class of the covering space. It's just a name for these homomorphisms. This actually turns out to be a functor of categories if you understand this group as a category, but not very important at this point. And so basically, in the end, what we have proved is that covering spaces can be classified by a single characteristic class. By the value of this characteristic class, which is defined universally for all covering spaces. Its value in this group, as long as F is fixed, right, completely describes what our covering space was. up to an isomorphism. So actually, these are all iso classes, right? I'm classifying isomorphism classes of covering spaces. Okay. And the big part of part 3 of the seminar, again, if that ever happens, is extending this idea to classifying general fiber bundles, right? Because it will turn out that in general, one characteristic class is not enough to classify, to completely describe the structure of a bundle, of a fiber bundle in general. But for covering spaces, only one is enough. Okay. With that, let's talk about fiber bundles.
All right, so just start with the definition of fiber bundles once again, in case you don't remember. Recall that a map in a smooth map from manifold E to manifold M is called a locally trivial fibration. If it is a smooth surjective submersion, well, I don't need to mention smooth, surjective submersion, and it is locally trivializable in the sense that for every point P in M, there exists an open set U of P and a diffeomorphism chi such that the diagram commutes. Yeah. So essentially, for every open set in M, the fiber above the part of the space above M can be trivialized into a Cartesian product. And in particular, if this open set U can be made the whole manifold, the fiber bundle is said to be trivial, which means that it's just isomorphic to a Cartesian product of the manifold with something else. Diffeomorphism. Isomorphism in the category of smooth manifolds. All right. Also, for any point P, pi inverse of P is called the typical fiber. And all of these sets are diffeomorphic to one another for every P. Standard example is a covering space, which is something we've already seen, where the typical fiber is a discrete set. Or rather an at most countable set with discrete topology. So before the next example and before finally touching upon a little bit of physics, let me prove a theorem. Well, not prove a theorem, just mention a theorem. This is the Erasmus fibration theorem. And the theorem basically gives you a way to figure out if a map between two manifolds is a locally trivial fibration or not. Essentially, if you have a fiber bundle, it's a sufficient condition. It's not a necessary condition. So, if a map pi from E to M is a proper surjective submersion, then pi is locally trivializable, or is a locally trivial vibration. Or that. The proof of this is very technical, so I'm going to skip that. But for a lot of examples, it just suffices to see that if in particular, if E and M are compact, it just suffices to check if the map that you have is a surjective submersion, in which case you automatically have a fiber bundle. So that's the corollary. Mm-hmm. The inverse image of a compact. If the inverse image of a compact subset is compact, then the map is proper. So surjective submersions between compact manifolds are fiber bundles. So with this theorem, we can consider our first non-trivial example of a fiber bundle, which is not a covering space, which is the example of a qubit. All right, so recall that if you have a qubit, it's basically defined by a Hilbert space, which is equivalent to two complex numbers. A typical element is given by alpha comma beta, both of which are complex numbers, but states in quantum mechanics are normalized. So you also have mod alpha squared plus mod beta squared is equal to 1. And along with this, you also have invariance under a global phase. So if you have two different states that only differ by some global phase, the two of them are supposed to be identified. So you have e to the I theta times alpha, e to the I theta times beta is equivalent to alpha comma beta for all alpha beta in the set of complex numbers. So this is just the complex plane, which is isomorphic to R4. This expanding out alpha and beta into components tells you that this is a 3-sphere in 4-dimensional Euclidean space. And modding out this 3-sphere by this equivalence relation gives you a 2-sphere. And the way to see that is to consider the quotient map, pi of alpha beta is equal to mod alpha squared minus mod beta squared as an element of the real line, comma 2 alpha beta star, where star is complex conjugation, as an element of C isomorphic to R2. So this whole thing, the image of this quotient map is an element of R3. However, if you take the square sum of these components, so if you add mod alpha squared minus mod beta squared plus mod 2 alpha beta star squared, you can use the fact that the qubit is normalized to show that this is equal to 1. And this normalization implies that you have a unit sphere in R3, which is just an S2. So pi is then a map that takes in an element in S3 and spits out an element in S2. It's very easy to check that pi is a surjective submersion. S3 and S2 are compact, so this is a fiber bundle. This fiber bundle is not known as the Hopf vibration or the Hopf bundle. usually written as S3 superscript S1 to S2. This S1 is basically the typical fiber of the bundle, which is the set of all these global phases. So you're modding out by all the global phases from identifying every 2 points in S3 that differ by a global phase to get an S2. So which implies that the typical fiber above any point in the S2 is going to be a circle. Also, you can this is not equivalent to just S2 cross S1, so it's not a trivial fibration. And the easiest way to see that is to compute the first fundamental group of S3 and compute the first fundamental group of this Cartesian product. In this case, it is trivial. In this case, you get the set of integers just by how fundamental groups split over Cartesian products. So qubit is a fiber bundle, and that's about it. That's all the physics we'll do.
So why did you introduce S3 at all? Didn't you start with something that was simply S2 to begin with? Like, because alpha and beta
are complex numbers.
Yeah.
So they have two components each. So that's a sum of 4 squares, which is 1, which is an S3.
So you're saying before any restrictions, you have S3.
Yeah.
And then you apply restrictions.
Yeah. Just the normalization condition gives you an S3, and then identifying the global phase gives you an S2.
Oh, I see. So you do impose the first.
Yes.
Yeah.
Oh, so this S2 is simply just a block sphere. And this is how you deduce that the qubit is basically a block sphere once you identify all the global phases. All right, that's all the physics we'll do today. We start with another definition. Bundle morphisms. I'm actually confused by the picture myself. Can you do that?
How do you draw the threes here? We don't have a four-dimensional space, so people usually use stereographic projection. Right? You can take the two-sphere projected onto a plane with the pole going to infinity. If you do the same for S3, you can project S3 onto the three-dimensional space with one pole going to infinity. Right?
It's a series of growing spheres.
Right? So it's not a big deal. So if you draw the Hopf vibration in terms of the stereographic projection, it's going to be a vibration of the three-dimensional space by circles. And that's what's drawn in this picture, right? And one of the circles is going to be the vertical infinite line, straight line of infinite radius. That's the circle that goes through.
So it's a sequence of circles that grows and rotates and hence covers the entire three-dimensional space.
And it turns out that any two circles in this bundle are, in this representation in 3 dimensions, are linked with each other like
that. That hasn't helped me yet. But yeah, right. So let's say you have 2 fiber bundles. E projected down to M through pi, and E prime projected down to M prime through another map pi prime. And you can construct morphisms between these 2 bundles by using 2 maps, and H tilde, H from M to M prime, and H tilde from E to E prime. And this is called a bundle morphism if this diagram commutes. So basically, if these maps preserve the fibers above every point in M and M prime, the fiber above M gets mapped into the fiber above M prime, so that H composed with pi is equal to pi prime composed with H tilde. All right. Standard terminology for this is that H tilde covers H. All right. With bundle morphisms, we can also define the category of fiber bundles, FP infinity as the category of smooth fiber bundles, with the infinity stands for smooth, with bundle morphisms as the morphism between them. Similarly, you can also restrict to your base space by saying that H has to be the identity map between M and M, the same way we did for covering spaces, and define the category of fiber bundles over smooth fiber bundles over M. So with H equal to the identity map from M to M. And one more definition that we'll use later is that of a Lie group. A Lie group G is a smooth manifold plus a group. What properties do you think I need to add to make everything consistent? Right. So the multiplication from G cross G into G and inversion from G to G are smooth. And requiring both of these properties is equivalent to just requiring smoothness of one particular map. So equivalently, you can require the map G comma H going into GH inverse to be smooth. And this is both necessary and sufficient for both of these. All right. So like now that we've defined bundle atlases, it becomes more convenient. Now that we have defined fiber bundles, we need to figure out a way to do like actual calculations on fiber bundles, the same way we did for manifolds by defining atlases. So in order to locally distinguish between points in fiber bundles, we define a bundle atlas. So let's say you have a fiber bundle E by M with a typical fiber F and an open cover U alpha of the base manifold, such that the fiber bundle restricted to each of these open sets, this is defined as the fiber bundle pi inverse U alpha by U alpha, such that each of these sub bundles are trivial. Right, right. Aren't restrictions of bundle sub bundles? Oh, okay. Mm-hmm.
So we can invert construction analogous to some manifolds we have. Is it, what is meant by such we do something analogous to some manifold?
Right. You don't change the base space. Okay. All right. So In other words, saying that these restrictions of bundles are trivial implies that there exist diffeomorphisms chi alpha for each alpha from the restriction of the fiber bundle to u alpha into the Cartesian product u alpha times f, because the typical fiber still must remain the same. Every fiber is diffeomorphic to it. And these are called local trivializations of the fiber bundle. And then you have these sets of maps, u alpha, comma, chi alpha, sets of open sets and maps, which are called the fiber bundle atlas or the bundle atlas for E pi n. Mm-hmm.
First of all, this lecture is probably going to be like the most conceptually loaded this entire part.
Yeah.
Including the future lectures. So it's difficult. But like for this, it's a very important definition. Think of the Mobius band, for instance. The Mobius band is a bundle of its circle. Okay? Over draw the equator, the middle line along the band, right? And project onto it, or perpendicular to it along the band. That's going to be a bundle of its circle. And it's not trivial, we know, because it's not the same as the cylinder, which is the trivial bundle. But you can cut it into two parts, right? Like imagine cutting it in two different places. Or even one.
Draw it back.
And then you have trivial over a measure. So now this must be possible for unifiber bundle, right? Because unifiber bundle by definition is locally trivial. So if we cover the base by sufficiently small neighborhoods, the bundle will be trivial above each of them. Globally, it might not be trivial.
Right.
And trivial means the same as the product, or diffeomorphic to a Cartesian product.
Right.
So above each of those places, we have a diffeomorphism of that kind onto a Cartesian product with the fiber. Right. And that's the bundle atlas.
So one way of thinking about just visualizing a fiber bundle is you have this base space M, and at each point in the base space, you attach a copy of the typical fiber F. And in some sense, you have this means of gluing adjacent typical fibers together. So as long as you're working locally on the base manifold, you can always treat this collection of points on the base manifold and the collection of fibers attached to those points as a Cartesian product. But the moment you start thinking globally, the gluing can have non-trivial properties, and you won't get a Cartesian product anymore, like it happens with the Mobius band. Yeah.
So then, if everything looks trivial in the fiber atlas,
Mm-hmm.
so that non-triviality will show up in the fiber part.
In the transitions, yeah, which I'm going to define next. Mm-hmm. Yeah. So U alpha is the covering is a open cover of the manifold. So the union has to be M.
So I found out that the terminology is actually open covering.
Oh.
A cover is from covering space theory.
Yeah. Okay. I'll try to keep that in mind. All right. So it's an open covering of M, so which means that it has to cover all of M. And since each of these chi alpha are a diffeomorphism between the restriction of the bundle and U alpha cross F, they all ultimately cover all of the bundle. All right. And a second requirement for the bundle is for a bundle atlas is that pick any point M in M or in U alpha. Actually, U alpha beta, which is the intersection of U alpha and U beta. So if you want to consider a corresponding point M comma F in E, This can be trivialized in one of two ways, depending on which trivialization you use. And so you can construct the composite map chi. On E restricted to U alpha beta, which is diffeomorphic to the Cartesian product of U alpha beta and F. So F would be an element of the typical fiber above U alpha beta, and M is just this point. Right. Right. So F is in capital F, and M is in U alpha beta. Yeah. So that's exactly the point. So you can construct these composite maps. Chi beta composed with chi alpha inverse from U alpha cross F into U beta cross F. Right. So U alpha beta viewed as a subset of U alpha, and on the right hand side, U alpha beta viewed as a subset of U beta. That takes an element M comma F in U alpha beta across F as a subset of this, and maps it to what should the first element be? M itself, because that point shouldn't change. And the second element, however, can differ. It can be some function of M and F. And these T alpha betas are called the transition functions. So the requirement that we have on these transition. Right, I'm doing that. So the the requirement that we have on these transition functions is that T alpha beta for a fixed M, and by leaving the second argument open, is a map from F to F. And this map must be a diffeomorphism. So it must belong to the diffeomorphism group of F. So I don't know. So there's a little subtlety here. They also have to be smooth in some sense. But the trick here is if you treat the diffeomorphism group over F as a Lie group, it's some sort of infinite dimensional Lie group, which means that we'd first have to define infinite dimensional manifolds, but there's a way to do that. And once we define it appropriately, these T beta alphas must be smooth under such a definition.
Is this still the definition?
Yes, we're still defining bundle atlases.
Maybe the second question is premature then, but do all type of bundles have bundle atlases?
Yes, you can show that.
No, I mean, all we do is it's just local triviality. Right? All bundles are locally trivial.
Yeah.
Therefore, we can always predict covering of the base such that it's trivial above every of those open sets.
Oh, yeah, that's right.
Exactly.
And then you have that.
Exactly. So like the ingredients to define a bundle atlas are A, an open cover of the base space, B, a bunch of local trivializations, and C, all of these transition functions that are defined through the local trivializations. Yep.
Perhaps this is obvious, but so, and we can be assured that the typical fiber emits this construction.
Oh, yeah, exactly. Exactly. Mhm. Yes, you can. But all you need is one to define a bundle atlas. So for each fiber bundle, you can have different bundle atlases. Let's see.
Wait, an example of what?
of different bundle atlases for a fiber bundle. Yeah, right. That's a very trivial example, but
you can cover the circle by different open sets,
right.
That's a way choice.
No, but even for a given open set, there can be more than one different trivializations. Or can there? Yeah. Yeah. The only example I can think of is like for the same open cover and different trivializations are like if you have the typical fiber as a real line, any diffeomorphism on the real line will give you a different local trivialization. But
Take this one,
yeah.
Right, take this one, break it up into two parts. One open, that's the part above U1, this is the part above U2. They overlap over two little open sets. Then each of these parts you can map onto a direct product of an interval times the line. And you can imagine doing that in two different ways, right? You can do it either like an identity, like projected onto a wall, like that, right? Or you can also flip vertical, for instance. Those are two different isomorphisms, right? And those will give you two different atlases.
Right. What's that?
Yeah, you can do even more weird stuff.
Exactly. All right. So once we have a bundle atlas, we can start. The reason we work with a bundle atlas is because it makes it easier to do calculus and like stuff like relativity or whatever. You can have coordinates for the entire fiber bundle. And of course, in order to translate between different patches, you have these transition functions. Right. An additional point, if it is possible that all these transition functions could take values in a subgroup of M of the diffeomorphism group. So in that case, wait, what?
Is that we can think of these T beta alphas
Mm-hmm.
as not functions from M cross F into F.
Yeah.
But as functions from M into the group.
Yeah. Oh. Oh, right. So in this case, you can think of T alpha betas as functions that take in a value from the base space, a point from the base space, and spit out a diffeomorphism on the typical fiber. So that's how you view these transition functions. Sure. Yeah. All right. So in the case that these T alpha betas take values in a subgroup G of diff F. Yeah. I mean, for T beta alpha, it would matter because like depends on which one is inverted, and so T alpha beta is the inverse of T beta alpha, but for you it definitely doesn't. It's just an intersection. Yeah, exactly. All right. So in the case that these transition functions take values in a smaller subgroup of the diffeomorphism group, this G is called the structure group of the fiber bundle. Yeah, you can show that this will be independent of what bundle atlas you choose. How do you show that though? That the structure group is independent of what bundle atlas you're choosing.
If you choose the atlas such that it takes values only in a smaller subgroup of the photo, that becomes the structure group. So it's an atlas.
Oh.
Oh. That's called obstruction. How small can you make that? Is a big question that's related to classification.
Right.
If we can make it trivial, it's certainly we get this.
Exactly.
The G should be a least subgroup as well.
Yes. So actually, I should introduce this notation. This is so now this less than symbol is the symbol for a Lie subgroup. So a Lie subgroup is a subgroup of a Lie group that is in itself also a Lie group. So and an embedded submanifold. So once it's an embedded submanifold, you can just directly induce the smooth structure from the Lie group to make it a smooth manifold. All right. Okay. So G is the structure group of the fiber bundle, and so if this fiber bundle with structure group G is isomorphic or isomorphic in the category of fiber bundles to a fiber bundle with structure group H, which is a subgroup of G, we say that there is a bundle reduction from structure group G to structure group H. Yep, soon enough. All right, so these transition functions have a few conditions on them. That are induced by the fact that they are defined as chi beta composed with chi alpha minus. You have T alpha alpha is the identity function on F, the identity diffeomorphism, and T alpha beta composed with T beta gamma composed with T gamma alpha is also, well, restricted to U alpha beta gamma. The intersection of all three open sets is also the identity diffeomorphism, and this condition is called the cocycle condition. It's easy to see this from the definition of just chi, T alpha beta in terms of the chi's.
And then you can ask whether why don't we list more? Compose four of them in a cycle, etc.
Yeah.
That actually all follows.
Just from cocycles.
Is this equivalent to saying if we choose an open set, or we choose a point, then all of the diffeomorphisms from all the different, all the different charts in our bundle have to be transited?
Mm.
Okay, yeah, I guess.
It's just sort of it's a very trivial
Yeah.
way that you just ask, think about what these transition times do. But the question is like, how arbitrary can I make? Right? If I want to replace my definition of what a bundle is, instead by specifying the atlas, the transition functions, as opposed to specifying the bundle,
Exactly.
then how arbitrary can I make my transition functions? And it turns out
This is.
otherwise they will not be transition functions being bundled.
Yeah. All right, so that's literally the next thing. So with the bundle atlas, we can have an alternative definition for fiber bundles. And in order to define fiber bundles from bundle atlases, you need a bunch of things first. So you have the ingredients, which are a Bayes manifold M, a typical fiber F, which is also a smooth manifold, a Lie group, which is going to be the structure group G, which could be the group of diffeomorphisms of F, but if you want to consider some sort of reduction, you can always consider a group that's smaller. and a smooth, yeah, and a smooth. Oh, is that a theorem? Being able to reduce to a finite dimensional, or only in practice? I suppose, yeah. And a smooth homomorphism or a representation are from G into diff F. So in principle, G could be an abstract group, doesn't have to be a subgroup of the diffeomorphisms, and this ensures that it'll have some sort of action as diffeomorphisms on F. And a couple more things that I'll write there. So you need an open covering U alpha of the base manifold, and finally transition functions which form a cocycle, d alpha beta in C infinity U alpha beta comma G. So these transition functions, of course, have to agree with the two conditions, have to obey the two conditions. And then using these ingredients, you can define the total space of the fiber bundle E as a topological space as the quotient of the disjoint union of Cartesian products of U alpha with F, modded out by tilde, where, all right, what do you think tilde would be? So like each element of this is going to be of the form M1, F1. Another element will be M2, F2. When should I identify these two?
The points are the same, F1 and F2
Just diffeomorphic, or
wait, F1 and F2 are
wait, yeah, what do you mean diffeomorphic?
how should F1 and F2 be related?
Yeah, I mean M1
The same point.
equal to M2 is correct. And what else? Right, exactly. And if F2 is some T alpha beta acting on, let me call this M, T alpha beta acting on F1 at M. So this defines the equivalence condition, and the equivalence classes of this disjoint union under this relation is going to be the total space of your fiber bundle. But do you see why this is important? Because this equivalence class essentially gives you a way to glue different patches together. So if you have two open sets, U alpha and U beta, this disjoint union would just be some fiber over U alpha and some fiber over U beta, but you want to patch these two fibers together so that wherever the two of them intersect, you have this way of transitioning from one patch to another. And gluing these patches together gives you your total fiber bundle. And that's what this equivalence condition does. That's what the transition functions allow you to do. They help you patch things together. Okay.
Easy way to think about this.
Oh, yeah. But so what the group, you can think about the group. I think the easiest way to think about the group is just through its action on F. So like if you go back to the example of covering spaces, what the group all the group does is permute the typical fiber above every point. In this case, the fiber is a smooth manifold, so it acts as a diffeomorphism on that. It sort of molds it in some way, just shuffles around points in that typical fiber. Are maps from the typical fiber to them itself.
So think of the definition of the manifold, right? Remember that you cover the manifold by open sets, and each open set is mapped into N by the chart maps. And then you have transitions. These phi alpha inverse goes with phi theta. They were mapped from Rn to Rn, which were diffeomorphisms of open sets, right? So I could say, instead of describing them as maps from Rn to Rn, I could just say they are elements of a group of diffeomorphisms of open sets in Rn. Diffeomorphisms in general form a group composed of diffeomorphisms. So in that sense, just a rephrasing. But here, we have a bundle. Above every point we have a fiber, and the bundle is locally trivial, which means that in the neighborhood of that point, we can diffeomorphically map the bundle onto a direct product. But that operation is not unique, right? It's like a chart once again. So the non-uniqueness, only what it does is it shuffles the point in the fiber in the unit, right? Because I can take my fiber, map it onto the direct product. The base point is fixed, but in the definition, I have M to M itself. But what I map the elements in the fiber to in F is not fixed. That can be any diffeomorphism, right?
You can also physically think of it as sort of gauge. Like if you're in a trivial fiber, think of a gauge field living in your fiber. So if you have trivial vibration, like just a charge, right? You can put a vector potential, take some value in R everywhere in space. If you have a direct monopole or something, you can't write a gauge field in all of your space that describes the magnetic field from that thing, so you have to patch it. And the thing that you use to patch it are gauge transformations, which live in the structure group.
Right. So like just think about having a gauge field on a sphere, on the surface of a sphere. If you have a electromagnetic potential on the surface of a sphere, you can't universally define it everywhere. If you try to do that, it'll blow up at some point. Just say for a constant magnetic field. So the way you get away from that is by taking two patches of the sphere, defining non-singular electromagnetic fields on each patch, and then requiring that on the intersection, the two definitions should agree up to one of these transition functions. So that's another way of thinking about the group G. Any other questions? Yeah.
So the structure group, like what it does is it maps, it just shuffles points in the fiber, in the typical fiber. Shuffles points in the typical fiber. That's how it acts on the fiber, right? But it's not like it doesn't intrinsically exist in the bundle itself, because the bundle is nothing being shuffled in the bundle. It's just a question of how do you locally map the bundle onto a direct product with the fiber, and that operation is not unique. So there's a shuffling freedom in the F on the right hand side of all of those maps. So it's sort of non-intrinsic to the bundle.
Yeah. It basically shows up because we're trying to label every point on the bundle using coordinates, which we can only do locally. So we need to figure out how to map between two local descriptions of adjacent patches. And that's where the structure group comes in. Right. Yep.
I knew that would be a warm rabbit hole.
We'll get to that in part 3.
I've opened Pandora's box.
There's many examples
examples. Yes.
Yeah. let's wait for part 2 to end to get there. All right. Yeah. Right. So we've defined the total space, and we need one more thing to define our fiber bundle, which is the bundles, the submersion pi. And this can be defined as, so when you have this disjoint union of Cartesian products, for each element in this disjoint union, you'll have a canonical projection onto the first component. And upon taking this, upon quotienting by this equivalence relation, each of those projections will descend down onto E. So that's just the descendant of PR1 onto E. Okay. And then there, one can show that there's a, so this, we define E only as a topological space, but for a fiber bundle, we need a smooth manifold. And one can show that there is a unique smooth structure on E that makes pi a surjective submersion. So let me just write that down. And with that smooth structure, we finally have a fiber bundle the way we defined it before.
You can define a fiber bundle either as a manifold with projection, or you can define it as base manifold with fiber and a cosine.
The latter is how physicists usually define it because we like working with coordinates. The former is, yeah, exactly. Even if you want to do like calculus on any of this, you always have to consider some sort of bundle atlas. All right.
So the bundle atlas doesn't actually give us coordinates if we define it. Like if normal atlas as well.
Yeah. So for the open cover, you can get a normal atlas on the base manifold, and coupled with that, you'll have a bundle atlas.
Yeah, I mean, this maps you to U alpha to M and F, and then from there you can go.
Exactly. All right. Right. So in terms of this bundle atlas, we'd seen bundle morphisms earlier. So let's say we have a bundle morphism between two fiber bundles, EM and E prime M prime, projections pi and pi prime. So we had a set of points, two maps H and H tilde between M and M prime and E prime. And let's say we have bundle atlases on E on this fiber bundle as a collection U alpha comma chi alpha, and a bundle atlas on this fiber bundle as the collection U alpha prime chi alpha prime. And we want to see what these H and H tilde look like in these bundle atlases. And the way it goes is H tilde can be treated as a map in chi alpha inverse of P and F. Remember that chi alpha sends the restriction of E to U alpha into a Cartesian product. So chi alpha inverse takes in an element of the Cartesian product of U alpha and F and spits out an element in E restricted to U alpha. And then you can take that and map that into E prime through H tilde. And the requirement is that, well, you can show that this would agree with chi beta prime inverse of H of P G hat alpha beta P acting on F for yeah, this defines g hat alpha for a bunch of g-valued functions. G hat alpha beta from u alpha into g. So the bundle morphisms between two fiber bundles can be represented by these g-valued transition functions. Well, not transition functions, just functions between bundles. Oh, wait, let's see. Oh, I see. So I forgot to add an assumption here. I'm assuming that both of these bundles have the same typical fiber F and structure group G. Right. What's that? I don't think so. Yeah. So, like, just to unbox this complicated formula, I'll draw a diagram as well. So you have E. Exactly. So, like, I mean, you could consider, instead of g-valued functions, you could consider just elements of maps from f to f prime, but like, I don't really see the point of it. Right. So you have, let's say you restrict the fiber bundles to u alpha and to u alpha prime. And then you have these local trivializations that map into the Cartesian product. This is chi alpha inverse, and this is chi alpha prime inverse. This is going to be u alpha prime cross f. And what you want for a local representative of h tilde is a map here. And what that map does is takes points in u alpha into points into u alpha prime through h, through a local representative of h, and takes points in the typical fiber here to the fiber here through these g hat alpha betas. So local representatives of h are automatically defined by atlases on M and M prime. So the only additional information you need to characterize this map is these g hats. Does that make sense? Okay. So then we have a theorem. So let's say you have two fiber bundles over the same base space, E and E prime with submersions pi and pi prime. And we want to see if E is isomorphic to E prime. And this theorem says that this is true if and only if there exists a covering U alpha of M. Should probably write this somewhere else. I'm going to write that here. So you have two bundles over the same base space, E and E prime, and E and is isomorphic to E prime if and only if there exists an open covering U alpha of M and cocycles T alpha beta of E and T alpha beta prime of E prime. And finally, G-valued functions, lambda alpha from each U alpha to G, such that the cocycle of the second bundle, the transition functions of the second bundle at a point P can be written as conjugations of the transition functions of the first bundle. Well, not exactly conjugation, but like, so lambda alpha on the left and lambda beta inverse on the right. Right. Does that make sense?
So what's the meaning of lambda? So we may not choose sort of compatible diffeomorphisms on the same patch, or we might not choose the same map fiber, same patch, but we make them. Right. So the freedom in the choice of these lambdas is the freedom in the choice of local trivializations of the
Exactly.
chi alphas. Like chi alphas are not unique. So the question is,
So think of the T alpha betas. If you write the T alpha betas as some chi alpha composed with chi beta inverse, this product just takes chi alpha to lambda times chi. So all it's doing is like giving you this explicitly making the dependence, making the non-uniqueness of the trivializations explicit by saying that you can take any trivialization and map it by another group valued function. And if that gives you the transition function to the second fiber bundle, you can say that the two of them are isomorphic.
how do people need another comment? I'll take the complete. So you have these local trivializations above these guys, right? Above every small restriction of the bundle, local trivializations. But there's freedom in choosing them, right? These could be arbitrary diffeomorphisms, basically, between these two things that fix the base points. The question is, how different are they? How different are the different possible choices of these chi alphas? Okay? And we've basically described the difference here. Right? We showed that every morphism of bundles is locally represented by multiplying by a group element on the fiber. Okay. But I can shuffle the points in the fiber, right? I can reparameterize the fiber, which is basically the same as inserting a group element into here before acting on F with anything else. And that's still lambda, in this case, beta. I can insert that into here as part of my definition of the local trivialization. Right? And I can do the same here. I can insert a lambda alpha. Arbitrary. And both of those lambdas, all they do is just they reparameterize my fiber in these maps, in the definition of these maps. Right? Which would be the same as modifying the chi alphas in the fiber. And so when I insert the lambda here and the lambda here, that's equivalent to just conjugating this G by lambda beta and lambda alpha inverse. This G? Yeah. Group element function. This statement was showing that any bundle morphism can be represented as by G value functions. The structure group. Let's say diffeomorphisms of F. The group of all diffeomorphisms.
You remember how?
Yeah. No. So think what a morphism does. Right. Let's say
this is the same manifold, and H is just identical, okay, for simplicity. So then I'm mapping, let's say, a cylinder to itself, right, while fixing the circle. What can I do? Well, I can shuffle, I can deform it somehow vertically, right? Shuffle the points inside of each fiber. What is that? It means inside of each fiber, inside of each straight line on that cylinder, the vertical straight line, I'm applying a diffeomorphism of that straight line. Right? I'm stretching it somehow vertically. But that diffeomorphism can depend on the line, on the point on the circle. Okay? So I have a function from the circle to the group of diffeomorphisms of the line. Okay? So if G is the group of diffeomorphisms of R, then I just said that any bundle morphism of the cylinder to itself is uniquely described by a G-valued function on the circle. Right? This is just a statement that the same is true for any bundle, only you have to do it locally. The cylinder is trivial, which is why I can do that by just one function. But here I have to break up my manifold into small pieces, and then on each small piece I will have a G-valued function whose only role is to shuffle around to deform the points in the fiber. Or in this case, if it's two different bundles, it can map points in the fiber above in one bundle to points in the fiber in the other bundle. But it's still a diffeomorphism of F, an element of this group. Okay.
Yeah, this takes a while to get used to. All right. Any other questions? All right. So before we start the next example, let me just define one more thing. And essentially, the same way that we can define measure zero spaces without defining what a measure is, I'm going to define curvature zero spaces without defining what curvature is. So we have a flat bundle. So a fiber bundle is flat if it admits a bundle atlas with constant transition functions. Do you have a question?
Yeah. So this is bundle atlas basically induces the kind of trivial parallel transport.
Yes, exactly. So if you have, let's say, a curve going through a bunch of open sets that loops back to itself, whatever. So let's say it starts here, goes through these open sets and comes back. At each transition point, and let's say you have some sort of fiber associated with, so a point in the fiber above it, somewhere here. As you move along this curve, you want to figure out how this point in the fiber transports. And because your transition functions are all constant, this point in the fiber just shifts by some constant, shifts again by a constant. Think of the fiber, for instance, for the simplest example, think of the fiber as a vector space. So you have a yeah. So you have a point in the fiber. As you move from this patch into the other patch, this point in this fiber will transition to a point in the fiber above this patch. Okay. All right. So let's say you have a bunch of open sets, U1, U2, going all the way to UN, which is back to U1 again. And you have a point, P, comma, F, where P is in U1, and F is in the fiber above U1. And you have a curve that goes through this. It starts with at this point. So as you keep moving,
So let's say the path is completely contained within you.
right?
Consider a very small path, right? How do I parallel transport elements if I points in the bundle along that path in the base? What would your suggestion for a prescription be? What does that mean? This is a product, so you're labeling things with points and points apply to them. So you just do nothing. So in these specific coordinates, right, with the given trivialization, do nothing to the second component. Right? The first component is just above the path. The second component stays constant, which is just horizontal, literally horizontal path in the direct path. Okay. Now, if the path crosses into another u alpha, what do I do? I need to make sure that my path stays continuous, right? So I can basically do only one thing. I go to the other coordinate nef above u2, which glues to the old coordinate in above u1, right?
So you have this equivalence relation between two different patches. You have an equivalence relation between u1 and f, comma f, and u2, comma f, which says that m, comma f in this is equivalent to m, comma t alpha t21 of m, comma f in this. So if you want to describe a fiber in the first patch, using coordinates in the second patch, all you have to do is consider this. So as you move this path along into the second patch, this goes into gamma of t, comma t21 of f.
And how does the fact that the transition functions are constant help? Well, if we have just two patches, then if we do something when we go from alpha to beta, we have to just undo it when we go back from beta to alpha. If they were not constant, your parallel transport, which is constant in one patch, would not be constant in the other one. Right. So
Exactly.
my path is described by a horizontal path lift above u1, it wouldn't be horizontal above u2, right, in these coordinates, which would break our whole procedure. So that's why it's important that these transition functions are constant.
Right. So
and so that gives you, and then as you go to u3, you multiply by yet another transition function, an element of the group, right? And you continue going ahead. And as a result, we have given a complete description for how to lift paths off of the base into the bundle, right? I can draw any path in the base, and I lift it to a horizontal path in the bundle this way. But the prescription depends on what? I mean, like, collectively, it depends on for all paths. What does it depend on? Right, so it depends on the specific choice of these constant transition functions, right? Seems to depend. Right, transition functions are not unique for a given bundle. We just proved that, right?
Right.
You can conjugate by the different lambdas. So I can introduce constant lambdas on each patch and multiply the transitions by them. And that will be another description for how to lift paths, right? Will it? I mean, it's the same in the sense that it's sparsely grouped. So will that path, the lifted path, actually be the same path in the bundle after I change my transitions?
figure out, right, whether this definition of horizontal lifts depends on the choice of atlas with constant conditions, or it depends only on the bundle itself. Okay. So let's say, so we take a path. Bundle. Take the path from here to here. Let's say this is the first section of the bundle. This is the second section. It's like an unwrapped cylinder, let's think, for Mobius band. And this is going to be my path. And I go from here to here. Well, in the local coordinates here, this path will be horizontal, the lifted path, right? In reality, it can be something, because I don't know how this maps onto here. Right? Now, when I go into the second one, I change the height of this thing, and this difference here is the T12, basically. Difference between these two levels. But this point still goes to the same point here, assuming I broke it up somewhere. And then I have another, and then it goes on horizontally here. And then I have another transition function that maps it back into the bundle. So what does this curve depend on? I just described the whole procedure to you. So it doesn't depend on the height, right? So not only does it depend on the transition functions, it depends on the trivializations themselves, right? Which is a lot. So it's not even the cocycle, it's the atlas itself that it depends on. So a very ambiguous procedure in general. But once you specify an atlas whose transition functions are constant, that is a word. You have a connection. Connection, as I said last time, is a prescription for how to lift paths from the base. And on the flat bundle, that means there's always a connection. And that connection is flat. What does that mean?
Okay. Maybe I should skip the example of like line bundles over S1 and go straight into connections. All right. All right. Whatever. No, given that you already started this discussion. The Mobius band. We'll do that in the next example. Yeah. Yeah. We'll see that. All right. So now so I think Alex mentioned last week that there are only two, up to our isomorphisms, there are only two line bundles over the circle. Line bundles meaning the fiber has to be the real line, and those are the cylinder and the Mobius band. And we'll prove it now. So let's say we have an S1, and we want a line bundle over R, which means in order to do any calculations with that, we'll have to pick an open cover of this circle. So I'll pick the following open cover. U1 is epsilon to 4 pi by 3 minus epsilon, which corresponds to an open interval that takes this segment. U2 is given by 2 pi by 3 plus epsilon for a small epsilon to 2 pi minus epsilon, corresponds to a segment like this. And U3 is 4 pi by 3 plus epsilon to 8 pi by 3 minus epsilon, which corresponds to the third, whatever segment remains here.
These are so, except at a few narrow points, there are exactly two.
Yeah, exactly. At every point, there are exactly two parts covering it. Oh, no, wait. Yeah, except for epsilon intervals around 2 pi n by 3, there are every point has exactly two intervals covering it. Mm-hmm. At what?
Or like the special points, if there's only one.
Yeah, exactly. All right, so we have a covering of our circle, and now we want to construct transition functions from different open sets to different open sets that that would agree with the cocycle conditions and hence give us a line bundle over S1. So as long as these transition functions are elements of the diffeomorphism group of R. Now, if you remember from like back when we introduced manifolds for the first time, the only diffeomorphisms that exist on the real line are monotonically increasing or monotonically decreasing smooth functions, which is the statement that this is a disjoint union of it has that the diffeomorphism group of R has two path connected components. The first one for which if F is a diffeomorphism on R, F prime greater than 0 belongs to the first component, and second one F prime less than 0. So these are monotonically increasing functions. These are monotonically decreasing functions. The first component is the one that contains the identity transformation x to x. Okay. Yes. So we're looking at line bundles over the circle. So we want the fiber to be R. All right. So now we want 3 of these transition functions. So we want to specify, we want to figure out how many ways we can specify T12, T23, and T31 so that they obey the cocycle condition. So this is how we'll do this. We first pick 3 G-valued functions. Lambda 1, 2, and 3, which will be, so we take, suppose we have 3 transition functions. We'll try to map them into any other possible isomorphic line bundle that we can get. And we'll see how many possible line bundles that we can get by simplifying these transition functions using these 3 maps, lambda 1, 2, and 3. So let's say lambda 1 is the identity transformation on the real line. So T12 is a map from U12 into G. This is U1, this is U2. So U12 is the little segment of the circle. So it takes this segment of the circle and maps each point here into a well, let me call this diff R, into a diffeomorphism on R. So we can take this and extend it onto all of U2 in a continuous way. So T12 is defined here. We can extend that up to here and call this extension lambda 2. So we define lambda 2 such that lambda 2 restricted on u12 is equal to t12. And the reason we do this is so that under this transformation by these three lambdas, t12 prime will be given by lambda 1, t12, lambda 2 inverse. Lambda 1 is identity. On u12, lambda 2 is equivalent to t12, so this cancels with this. So what we have is that this is simply identity on R. So we've simplified one of the three transition functions to just the identity function. And we can do more. So since lambda 2 is a diffeomorphism on R and it agrees with t12 on u12, lambda 2 must, on all of u2, it must have the same parity as t12. So if t12 has positive derivative everywhere, so should lambda 2. And if t12 has negative derivative everywhere, so should lambda 2. Similarly, we can take this u2. We can take the intersection of u2 and u3 on which we have t23 defined and consider the extension of this onto all of u3. And use that to define lambda 3. So we've already defined lambda 2. Lambda 1 is the identity. Now we're defining lambda 3. So now t23 prime under the same transformation is going to go to yeah, you did. Wait, what?
Lambda 3 is the extension to U3 of lambda 2 T23.
Oh, oops. Sorry. Yeah, no, I have that in my notes as well. I just missed that. Yeah. So because it's, sorry, you take the product of lambda 2 and t23 on u2, on u23 and extend it continuously to all of u3 and call that lambda 3. There's some extension. It may not be unique. We're just considering some extension so that this agrees. So the parity of lambda 3 is going to be the parity of the product of lambda 2 and the products of the parities of lambda 2 and t23. But the parity of lambda 2 we already saw was equal to the parity of t12. So the parity of lambda 3 is the product of the parities of t12 and t23. All right. So under this transformation, we have lambda 2 3 prime is equal to lambda 2 t23 lambda 3 inverse, which is lambda 2 t23 t23 inverse lambda 2 inverse. So this is also the identity on R under this choice. So we've reduced this to identity. We've reduced this one to identity, and all that remains is the third transition function. And this transition function will basically characterize all possible line bundles that we can have over a circle. All right. And similarly, t31 prime is equal to lambda 3 t31 lambda 1 inverse. Lambda 1 was just the identity transformation, so this is just lambda 3 t31. Okay, now so let's look at the parity of lambda 1 2 prime and lambda 2 3 prime are just identity, so they have positive parity, which means that their derivative is everywhere positive. Let's look at the parity of t31 prime. This is equal to parity of lambda 3 multiplied by parity of T31. But as we saw earlier, because of this definition, parity of lambda 3 is parity of lambda 2 times parity of T23. And parity of lambda 2 by this definition is equal to parity of T12. So this is just parity of T12 times T23 times T31. So it's the product of all three parities. Mm-hmm. Oh, the sign of the derivative. If the derivative is positive, the parity is positive. If the derivative is negative, the parity is negative. Right. Okay. So now, all right, let's see. So what's the best way to do this? So lambda 3, in order to fix, so T31 can have one of two possible parities, +1 or -1. And in order to fix T31 prime, we will fix lambda 3 in such a way that we can only have two options, which we know from hindsight. But so what we can do is we had some extension of lambda 3 from U23 to all of U3. So it was so lambda 3 is fixed on this intersection U23, but we can extend it however we want as long as it's continuous onto U3. Now, as long as we have some smooth extension, we can always deform it in such a way that on U3 minus U23, so that lambda 3 restricted on this part is equal to T31 inverse up to this parity transformation, where I define, what's that? Yeah. Yeah, exactly. Exactly. So epsilon is still finite. We're not taking the limit. Oh, this is U3 minus U23. Ah, okay. I see. Okay. Right. Where G plus is the G plus or minus of X. Mm-hmm. Yeah.
Here is so U3 minus U23 is minus epsilon. Wait, remember we have the little epsilons here. So
right.
U23 ends here. So this one starts with minus epsilon angle and goes to 2 pi over 3 minus epsilon. Okay. But this lambda, let's fix it to be that only on from plus epsilon to that.
Yeah, that's U31 or U13. Yeah. All right. So we have this.
But the epsilons, like if we were working in the continuous category,
Mm-hmm.
we need the epsilons because then you can just
Right, exactly. You don't care about the derivatives.
a little bit of space in the smooth category so that you can match the derivatives.
Right. All right. So we can always deform lambda 3 in this way. So what we ultimately have is T31 prime is then going to be, which is lambda 3 T31 is just going to be plus G plus or minus. So either the identity or, well, minus X. So there's only two possibilities for T31 prime. T12 prime and T23 prime were fixed. So you can only have two possible line bundles over the circle up to bundle isomorphisms.
And you just argue that if you had some bundle that required like more patches
Mm-hmm.
in this process. What do you mean by that? Like higher dimension? Well, if there was some line bundle of the circle that required more than 3 patches to describe it.
Oh yeah, all one-dimensional bundles will be sort of classified this way.
No, but I mean, we've just picked 3 patches over a circle. You can also like, if you have more patches, you can always reduce it to a subcover. But you can always convert it to a 3-patch atlas.
Classification of bundles doesn't depend on size of the
Yeah.
There's some bundles you can't or I guess you have to make some argument. Like always, I mean, there doesn't exist in the circle.
There's only 2 one-dimensional bundles as far as we're concerned, right? So, circle and line.
Exactly.
Pretty easy to classify.
It's also happens you really use two spaces instead of three. Then what happens?
Two spaces that are
Yeah, instead of three, so you need one and you do it so and there's no use.
Oh. if it's just 2. If you cover the circle with just 2 patches instead of, in that case, it should still work out the same. It's just that one of the transition functions can be reduced to identity, the other one is up to a parity.
No, it's just like if you take the Mobius fact, right, and
Yeah.
cover it by 2 things, then you'll have a transition function like U12 will be a disconnected set.
Exactly.
Consisting of 2 open sets, right? And on one of them, the value of your transition is going to be +1, and on the other one is -1. To add the twist, right?
So if you have,
Oh, so there's a constant transition function there.
Like you can do it, it's just not convenient to have intersections that are
disjoint. So I mean, you have the intersection U12 is going to be a union of these 2 disconnected components. So like you can still have smooth transitions on this disconnected components that can, take one value here and another value here. Right.
it wouldn't be enough to argue you can do all this.
Yeah.
He's saying that the argument goes through this case, but it's more complicated, and they just chose 3 patches because it made the proof cleaner.
Yeah. So that we can work with like connected intersections. Did you have a question?
So when you said a flat bundle,
Mhm.
flat could admit a bundle atlas with constant transition functions. So do you need to have only connect the transition functions, like the connected components of these are constant? Because you have
So
I believe it's 1. Just because that one is a constant doesn't mean it's not flat.
No, but it's enough, right? It's sufficient. Like it's an existence statement. So you can always pick an atlas
Yeah.
small enough so that the intersections are all connected.
If you can, so you just chop your atlas in.
Yeah, but you can replace that condition by locally constant.
okay.
Locally constant functions means constant unconnected.
yeah.
That was a definition, not a condition.
I mean, so basically, like, as long as you choose your cover correctly, you will like for not every cover. You won't have constant transition functions for every possible covering of the base space, but there will be some covering for which there'll be constant transition functions. Right. Um, wait for part 3. But yeah,
So in this case, like, you only have two. If we cover the space with just two segments, in that case, then T12 is still identity on the bottom part. It's minus identity. Minus identity on the top.
right. So that will give you a Mobius band, but if it's identity on both, that would give you a cylinder.
So this T12 is a double value function.
It's a double. No, it's not.
What's the value to take the top half of it?
Right, it's not a constant function, but it's still a single valued function. Like each point in on the circle only takes one value in the diffeomorphism group.
Exercise any bundle above a one-dimensional manifold, like you circle a line, is flat.
Yeah.
Doesn't matter what type. We took the line, but it doesn't actually matter. If you look at this argument, we never really used the fact that it's a line. We only used the fact
Exactly.
that the diffeomorphism of the line consists of two connected components.
Yeah, also like later, in order to check that whether a bundle is flat or not, you can come up with this curvature tensor and just show that the curvature tensor vanishes for depending on what sort of bundle it is. If it's derived from a principal bundle, then it's
Yeah, so
just
you
there.
take an important hint from this problem, right? That in classifying bundles, all that matters is the topology of the structure. In this specific case, it's only the number of connected components of the structure, right? We found that the number of bundles is equal to the number of connected components of the structure above the circle. What if it's above a higher dimensional manifold? What does it depend on? Turns out it depends on things like homotopy groups, homology groups of the structure group. And that's theory of characteristic classes.
Can you relate this to the fact that the circle has a curvature? Any smooth structure on the circle is a curvature.
That's the same statement.
Or sorry, in the differential geometry.
Anything above a one-dimensional manifold is flat, yeah, because curvature is a two-form. Yeah, there's no two forms on a one-dimensional manifold.
All right. I think it's a good stopping point. We'll talk about connections
Or you can
next
talk
week.
about connections for a minute.
It's not that quick.
But I want to do it.
Next week.
Come on.
Also, I have office hours in like 5 minutes, so I need to run.
What do you guys think?
You can talk about connections if you want. I'm out of here.
We can come to a full stop that way. I'll be quick.
Not for food, talking about it.
Just a couple of minutes. Well, no, but it's more, it's like a side, it's an aside thing, so. Right. Let me remind you what we did in covering spaces. Remember, we had that property that if two paths are homotopic in M, in the base, then this is if and only if their lifts are homotopic. So this is in covering spaces. If and only if their lifts are homotopic in the covering space. Okay, so that means if I have my base, two paths that are homotopic, and I have my covering space locally looks the same as M, then their lifts will also be homotopic. Okay. So now let's think about this parallel transport business, right? In the parallel transport interpretation, what does that mean? Let's say I have a hole in this manifold, right? And I pick a path that goes like that. Okay. We know that in the covering space, this path might lift to something that doesn't go back to the same point. Okay. Depending on what the covering space is and where we started, stuff like that. But what we do know is that if I deform this path a little bit here, it'll deform a little bit here, but the endpoint will not change, right? Because they're homotopic to each other, and this homotopy used in that theorem was with fixed endpoints. Okay. So if my endpoint here and starting point didn't change, then it's not going to change here too. Okay. So that property of this connection, of this instruction to lift paths, is called flatness. Right. So flatness is independence of small deformations of the path along which we parallel transport. Okay. Think of parallel transport of vectors in three-dimensional space, right? How does it work? Well, I take my vector and I literally just move it anywhere, right? And it doesn't matter along which path I do it. We know exactly how to do it in three-dimensional space because it's flat, right? So the question is, how does this generalize to bundles, to general fiber bundles? So let's define, let's say this is a bundle with a connection understood as a prescription for lifting paths. Right? Then I can define, let's say I have a point P and M. I can define this group. It's called the Holonomy group at P. And it's just equal to the following. It's all elements G in the structure group of this bundle, such that G is equal, such that there exists a path in M, such that G is the diffeomorphism in fiber that is obtained by parallel transport along gamma. Right. So I have this path in the base, and I can lift it with its starting point being any point in the fiber, right? And then parallel transport the entire fiber along that, right? So my fiber consists of many points. I can take every point, parallel transport along my path, and it's going to go to somewhere, right? Whatever. At this point, maybe we'll go to here.
These would form a point independent subgroup of that.
Right, so this is a map from this path into a diffeomorphism of the fiber, right?
So when you say parallel transport, what exactly do you mean? Like,
Parallel transport means just lifting the path and then moving, the points on the lifted path are called parallel transports of the starting point along the, just another name for lift, right? And then we take, gamma is a loop, actually, loop in M based at P, based at P. Based at P, right? So let this be P, and do parallel transport of the fiber above it along all possible paths in the M. The diffeomorphisms that you get from that of the fiber will form a subgroup of the entire group of diffeomorphisms. That's called the holonomy group. Okay. And then we also have holonomy tilde. That's going to be only G's along contractible loops. Okay. So the same thing, but not gamma cannot be any loop, has to be contractible. Right. So, and that's called local holonomy. Local holonomy. Okay. So in covering spaces, what is local holonomy? If I have a small loop that's contractible and a parallel transport along that, yeah, I always go back, right? Because we know if it's contractible, it's homotopy equivalent to a point, and the lift of a point is a point. Okay. In general bundles, local holonomy is not necessarily trivial, but definition, connection is flat if the local holonomy is 0. Well, by 0, I mean trivial for all p, for all points. So there's no non-trivial local parallel transport anywhere.
This also means that we can define flatness at a purely local level. Or not.
Well, given the connection, right? That's a big requirement. Okay. So I'm stating that from this point of view, flat bundles with a flat connection. So the connection that we've constructed before for a flat bundle, remember, for lifting paths, that one is a flat connection with the constant transition functions, right? That's a flat connection because the way we lifted it, it's horizontal in the direct product, and if I deform it a little bit, it'll still be the same horizontal. So like if it's a small loop, it'll come back to the same point. It'll have to because it's horizontal.
So by connection, do you mean the way in which you lift the path, so like the covering spread?
Yeah, by the connection I mean this prescription for lifting. Yeah, right. And the connection is called flat if I always go back to the same point when I parallel transport locally, right? Globally, not necessarily. Okay. So the connection that we've constructed before is flat, even though it's not unique, right? It's dependent on the atlas, on the choice of the atlas. So I'm basically telling you about this just to say that flat bundles with a flat connection are sort of natural generalizations of covering spaces, but now with uncountable fiber. Right. And we can even see the signatures of the covering space in this flat bundle. So basically, I'm claiming that if we have a flat bundle, then you can fibrate it locally, fibrate it into layers, each of which is locally diffeomorphic to M. Right? What are those layers? Right. Yeah. So I just take all possible local small paths in M, right? And I take any point in E, and I consider their lifts in E. And that's going to create, that's going to give me like a slice in E, which is diffeomorphic to M, you can show. And the reason it's diffeomorphic to M is because the connection is flat. So the result doesn't actually depend on the shape of this path. It depends only on the endpoint, right? Which means that this thing is literally just a copy of the set of endpoints of these paths, i.e. this neighborhood in M, right? No, not really. Yeah. So any flat bundle with a given flat connection gets fibrated into locally gets fibrated into copies of small neighborhoods on them. Right? The same idea as a covering space, only now it's in a continuous fashion, not a discrete fiber. And another way to think of flat bundles, so like, is there a way to forget about the flat connection and still think of a general flat bundle without a specific connection as a covering space? That's the question. I claim that yes, but you have to change the structure group. So think of what this does. You have, if you have a hole in here, you can go around the hole and get a non-trivial holonomy potentially from that, right? That would mean that if I extend this fiber around the hole and go around the hole, it doesn't glue to itself, it glues to some other fiber, right? That's what non-trivial holonomy would mean. By fiber, I mean these horizontal fibers, again, not the vertical ones. Layer, let's call them layers, okay? Now, I claim that if we replace G by G with discrete topology, then this prescription for lifting paths will be uniquely fixed by the fact that G has discrete topology and the structure of the bundle, right? Why is that? Well, because if G has discrete topology, then all continuous functions valued in G have to be constant, right? Which means that this would force my transitions to be constant. And that would force a specific connection, a specific flat connection, and a specific vibration into layers, right? So that's just another, I mean, it's not very important. It's another way to think about this without connections involved.
And then, so we can associate once we have that, once we have a flat connection, we can associate all the structure of it with relating the fundamental group to these transparations.
Right. So how is this connection, the flat connection, described in terms of the fundamental group? Is this holonomy, you can take the global holonomy and factor it by the local holonomy, right? And that completely describes my bundle, in fact. It describes my flat connection entirely, right? Because, because this thing gives you a homomorphism from pi 1 of M into G, right? I'm basically saying, if my loop goes around the hole, what's the diffeomorphism? What's the parallel transport on the fiber, right? And this factor exactly gives me that information, right? For every loop, I get an element of the group, structure group, right? And because it doesn't depend on the shape, on the homotopies of the loop, it's actually a map on the fundamental group, right? And this is the same as what I said in the beginning of the lecture about covering spaces, right? Covering spaces are classified by homomorphisms from pi 1 of M into the structure group of the fiber, the diffeomorphism group of the fiber, right? And it's the same for general flat bundles, right? So flat bundles, once again, are entirely classified by one characteristic class. This is called, right, this homomorphism is called the characteristic class of the flat bundle. But with connection, with flat connection. Right, because this thing in general depends on the connection.
So we can have flat bundles without specifying a connection.
Yeah.
And that was just the.
If you assume discrete topology on G. Yeah.
Doesn't that induce?
Discrete topology on G is sort of like discrete topology on the fiber, and then you go back to covering spaces, only now with uncountable fiber.
But doesn't that induce a unique connection?
Exactly. That's what I'm saying, right?
Oh, I mean, like,
But you don't have to talk about connections to define that. To,
okay, but like
yeah.
there's a one-to-one correspondence between flat bundles and like, for every flat bundle there's exactly one flat connection.
For every flat bundle with discrete structure group, there's one connection, flat connection. But if the structure group is not discrete, some continuous Lie group, it's not unique. The flat connection is not unique. And then the characteristic class will not be unique. Okay. So the big question for part 3 of the seminar is, how does this classification extend to general fiber bundles with groups that are not necessarily discrete topology, or bundles that are not flat, things like that. Turns out you cannot classify those bundles in general by just one characteristic class, by just one simple assignment like this. You need a whole series of characteristic classes, which are not actually homotopy related things, but homology related things. So that's why we have to talk about homology. Okay. It'll get much easier from now on, I promise.
Yeah. So the thing about like relating curvature in the transport sense to curvature in like the Riemann tensor sense, is that just some manifestation of the de Rham cohomology? You know, I definitely don't have the tools to even.
No, I mean it's a question of how do you describe a connection by differential forms.
Okay.
It turns out that a connection, instead of parallel transport, you can describe by a differential form. And then its exterior derivative turns out to be the curvature 2 form.
But is that?
And then that's the 2 form thing is 2 indices out of the 4 in the Riemann tensor.
Yeah. And then is it the Gauss curvature?
What?
The 2 form. Or no, sorry, the Gauss.
No. Total Riemann tensor is just a different way of understanding.
And is that like just a subset of like de Rham cohomology, or is that something completely different?
It's sort of related. I mean, everything's related to de Rham cohomology if you think long enough.
Okay.
So.
Yeah, and here we're mapping points onto the group itself, and so we're mapping all the different points onto that identity element of the group. In that case.
I'm not sure I understand what your question is.
We have to read that note first.
And do you understand why transition functions take values in the group?
Yeah, so it's like that in this case, and then he mentioned that we'll have transition function equals to identity. But if it is identity, it is not something to be constant.
No. It's a function that takes values in the group of diffeomorphisms, right? And it's constant and equal to the identity element in the group. Okay. It's a constant function whose value is the identity. It's not that the function itself
It's a
is the
function
identity.
from
Yeah,
points
yeah,
to
yeah.
functions.
Yeah.
Value function.
I thought at some point that could be confusing.
Okay. So it is like that because E equals to one function. So
Yeah,
it is
one
constant.
group
It is,
element. Yeah.
okay, I see.
Yeah.
Okay, question. Okay.
Or, yeah, constant in the sense that you have an